There are plenty of half-truths about rotary engines, like that they didn't have carburetors and had to run full throttle all the time, and that the spinning cylinders created such strong gyroscopic forces that rotary-powered aircraft were extremely difficult to fly. But what was the primary reason the cylinders spin in the first place? And why did the rotary go from powering the vast majority of Allied World War I fighters to obsolescence in just a few years? We'll cover the features common to all rotaries, then dive deeper into the peculiarities of the most popular ones like the Rhône, Clerget, Gnome, and why trying to fix the biggest problem of the rotary engine in the Siemens-Halske totally ruined it. By the way, I'm not covering the Wankel engine. I've done that already in a different video. This video is about the original rotary from World War I. In the early years of aviation before World War I, liquid-cooled engines were the norm. But liquid cooling was still very inefficient. These heavy engines required heavy radiators, adding weight and drag. They also carried a lot of water for cooling, especially compared to modern engines. The advertised weights of liquid-cooled engines were almost always given as dry weight, excluding the water and usually the radiator system as well. Air cooling wasn't realistically achievable due to metallurgical and manufacturing limitations of the time, at least for engines powerful enough for military use. But there was a way for a certain engine design to create its own airflow for effective air cooling, even with these limitations. That engine was the rotary, and the reason it was designed to spin was to improve cooling and allow it to be air-cooled. With a rotary engine, the crankshaft is bolted to the airframe and the cylinders spin around it. The propeller is bolted to the cylinders and the pistons move up and down over 360 degrees of rotation. This has massive benefits and drawbacks, which we'll cover in detail. Other than the spinning cylinders, rotaries operate on the same principle as a conventional 4-stroke engine. Rotary engines were very light for power produced, partially because of being air-cooled, and partially for their insanely thin-walled nickel-steel cylinders that are only 1.5 mm thick, each weighing less than 3 kilograms. Rotaries had an interesting way of getting air and fuel to the combustion chamber. A carburetor was located at the rear of the engine. Yes, most rotaries did have carburetors, but we'll cover that shortly. The fuel and air mixture moved through a hollow crankshaft to the front of the engine into the crankcase center, which acted as a plenum. From here, the air and fuel mixture was drawn into the cylinders where combustion was started by a spark. Rotary engines had an odd number of cylinders, 5, 7, 9 or 11, with the vast majority having 9. The reason for the odd number is simply to allow for an even firing interval, which for a 9-cylinder rotary is every 80 degrees of cylinder rotation. After firing cylinder 1, it fires every other cylinder in order. A smooth firing interval wouldn't be possible on 4-stroke rotary engines with an even number of cylinders per row. Of course, it's possible to use 2 rows, which does result in an even number of cylinders, but they always have an odd number per row. An example is the 14-cylinder Gnome Omega, though these double-row rotaries weren't very popular. The rotary engine was designed in the final years of the 1800s, and by 1909 it was the best engine type for aircraft, moving aviation from the early experimentation phase to mainstream use. The main benefit was its superior power-to-weight ratio. One weight saving was the absence of a flywheel, possible since the spinning engine was essentially its own flywheel. A 4-stroke engine produces power intermittently. The momentum of a spinning flywheel smooths out this intermittent power delivery, but makes the engine heavier. With the spinning mass of a rotary engine's cylinders, it didn't need a separate flywheel saving weight. The other saving was already mentioned, not needing a radiator system or water to cool the engine. This was possible because the spinning cylinders effectively created their own airflow. The roughly 1200 RPM these engines spun at cooled the engine very effectively, even with the aircraft stationary on the ground. But how much difference did this make in weight? The early Mercedes D3 that powered a wide variety of German World War I fighters produced 160 horsepower and had a dry weight of 278 kilograms. It also required a radiator which weighed about 16 kilograms and needed to carry approximately 23 kilograms of water. So the weight of a functioning engine was around 317 kilograms, giving it a power-to-weight ratio of 0.23 horsepower per pound. Even the very impressive Hispano-Suiza 8A's radiator system on the RAF SE-5 fighter weighed about 23 kilograms and carried about 30 kilograms of water, giving it a power-to-weight ratio of 0.27 horsepower per pound. The Gnome Monosoupape's 9N produced 160 horsepower from 154 kilograms, which is 0.47 horsepower per pound. Rotary engines feel smoother running than conventional engines because all the primary and secondary forces normally enacted up and down the cylinder now get distributed rotationally along 360 degrees of rotation and are thus mostly cancelled out. One of the earliest mass-produced rotaries was the Gnome 7 Omega, also called the 50 horsepower Gnome. It's a 7-cylinder rotary that first ran in 1908, manufactured by the French Gnome Motor Company. It produced 50 horsepower at 1200 RPM from 8 liters of displacement. As expected, it was lightweight at 75 kilograms. Quite importantly, these early Gnomes were the first aero engines able to routinely exceed 10 hours before requiring an overhaul. The Omega used a master and articulated connecting rod setup, as you'll find in a radial engine. To dispel one misconception, the Omega did have a carburetor located at the rear of the engine, but its induction system is probably its most interesting and unique feature. As you can see, it only had a single pushrod, and this controlled the exhaust valve. The cylinder head did not contain an intake valve. This led to misconceptions that all Gnomes were single-valve engines. But the Omega did in fact have 2 valves per cylinder. The intake valve was just not located in the cylinder head. Instead, it was located inside the pistons. This piston valve operated fully automatically, requiring no drive system. The valve closed by pressing down against the seat in the piston and opened by moving upward. When the engine was spinning, centrifugal force pushed the valve closed. This seems counterintuitive since you'd think centrifugal force would pull the valve open. But the valves had counterweights pivoting from the valve, meant to neutralize the centrifugal force and piston acceleration acting on the valve's mass. These weights were heavier than the valve itself, which pulled the valve closed. But how then did the valve open for intake? After the exhaust stroke, the exhaust valve closes and the piston moves down for the intake stroke. This creates a partial vacuum which pulls the intake valve open. The lightweight valve spring and counterbalance weights are engineered to keep the valve closed during operation, but allowed to open with the slightest suction during the intake stroke. The suction pulls in fuel and air mixture from the crankcase. At bottom dead center, when the piston starts the compression stroke, the pressure in the cylinder increases and the centrifugal force and valve spring combined pulls the valve tightly closed for compression, combustion, and exhaust strokes. This clearly worked well enough if they sold around 4,000 of these engines, not including the more powerful 7-cylinder Gnome Lambda and 100 horsepower 9-cylinder Delta, which used the same intake arrangement. But these Gnomes were far from problem-free. The correct setting of the piston valves was crucial for performance, and once the engine was assembled, the engineers no longer had access to make adjustments. Something else that caused a lot of maintenance hours was stuck valves, which happened often due to combustion contaminants. This is simple enough to correct on a conventional engine, but on the rotary it required opening the engine to remove the pistons. This contributed to the low hours between overhaul. Yes, it was the first engine to exceed 10 hours between overhaul, but just a few years later, engines like the Hispano-Suiza 8A exceeded 50 hours between overhaul. Things changed quickly, and the Gnome needed development to keep up. Gnome knew they had to get rid of the piston valves to improve their engine, but having 2 push rods per cylinder seemed too complex, and perhaps overcompensating for their intake valve problems, they decided their next rotary would have no intake valve at all. Their improved 9-cylinder rotary was called the Gnome Monosoupape, which is French for single valve. The 9B variant produced 100 horsepower and the 9N produced 150 to 160 horsepower from 12.8 and 15.8 liters of displacement and dry weights of 123 and 154 kilograms respectively. So, how did the Monosoupape's induction work without an intake valve? It used transfer ports at the bottom of the cylinder, which was exposed when a piston reached bottom dead center. Those familiar with 4-stroke operation may see the problem here. The piston reaches bottom dead center and exposes these ports not only at the end of the intake stroke, but also at the end of the combustion stroke. So how did it not combust the air and fuel mixture in the crankcase when the piston reaches bottom dead center during combustion? About 100 degrees after the combustion stroke starts, the exhaust valve opens to reduce cylinder pressure and temperature. Spent gas is exited via the exhaust port, and by the time the piston exposed the intake ports, the charge had mostly finished burning and was considerably cooler. In addition, this could not ignite the mixture in the crankcase because it was deliberately too rich to combust. It didn't pull in much new mixture at this stage, as the pressure in the cylinder and crankcase was now equalized. The actual exhaust stroke only started now. After the piston reached top dead center, the exhaust valve remained open for much of the intake stroke. As the piston descended, it pulled in fresh air, only air, through the exhaust port. The exhaust valve would remain open until just before the piston exposed the intake ports. Now the exhaust valve closes and the descending piston creates a partial vacuum. As the piston exposes the intake ports, the suction pulls the overly rich mixture from the crankcase into the cylinder, where it mixes with the air that entered via the exhaust port to create a combustible mixture. The elimination of the piston valves virtually doubled time between overall, but also increased fuel consumption considerably. The 9N consumed about 29 gallons per hour, or just over 1 pound per horsepower hour. One side effect of this unique intake arrangement is that this engine could not use a carburetor. This is the reason for the half-truth that rotary engines didn't have carburetors, but the Monosoupapes are the only rotaries that didn't. With most of the intake stroke drawing air through the exhaust port, with the transfer ports only briefly exposed at the end of the intake stroke, it couldn't use a conventional carburetor. Instead, it used a tamper valve, which directly metered liquid fuel into the crankcase. The fuel didn't fully atomize until it was sucked into the cylinder through the transfer ports. So the engine ran at full throttle the whole time, but there was some control over engine power. The first was fine control of fuel via the tamper valve. Reducing fuel effectively leaned out the mixture and reduced power. But this offered very limited control as it would quickly overheat the engine. The preferred method of reducing power was using a blip switch. The initial 100 horsepower Monosoupape B2 had a very crude blip switch that simply grounded the ignition, preventing all cylinders from firing, engine fully on or fully off. This could control the rate of descent when approaching for landing. The momentum of that heavy spinning engine, as well as the wind turning the propeller, kept it spinning, acting like a starter motor. All that was required to produce power again was releasing the blip switch, restarting ignition. Later Monosoupapes, like the 160 horsepower 9N, used a more advanced blip switch with 5 modes: full power, off, and 3 intermediate modes. The first intermediate mode fired every 4th cylinder instead of every 2nd. The second mode fired every 8th cylinder, and the last fired every 16th cylinder. This allows much finer control of engine power. The 100 horsepower Monosoupape 9B powered World War I aircraft like Sopwith pups and some variants of the Avro 504. and the 150 and 160 horsepower 9N powered the Meurisse Type A1 and the Newport 28 respectively. The 9-cylinder Le Rhone rotary is from French company Société de Moteurs Le Rhône, who in 1915 merged with the Gnome Motor Company to form Gnome at Rhône. The Le Rhône has two unique features. The first is how its valves operated. It has two valves per cylinder, both in the cylinder head, but only one pushrod for each cylinder. How does that work? Well, it isn't a pushrod, it's a push-pull rod that operates both the intake and the exhaust valve. By a central pivoting rocker arm, when the rod pushes up, it opens the exhaust valve, and when it pulls down, it opens the intake valve. This was accomplished with a linkage system at the cam ring. When the first lobe reaches the main wheel of the rod, it pushes the rod up, opening the exhaust valve. When the cam lobe reaches the secondary wheel, it pushes it up, and the rocker pivots, pulling the rod down. This closes the exhaust valve and opens the intake valve. This complex system was introduced to halve the number of push rods on the engine. A distinguishing feature of the Le Rhône rotary is its copper induction pipes. Different from the Gnomes, the fuel and air mixture was drawn by suction steering the intake stroke via copper pipes from the crankcase. The Le Rhône also had a very different way of connecting the connecting rods to the crankshaft. All the other rotaries discussed here used a master and articulating rod setup, where the master rod is fixed and hosts a spider hub where all other rods swivel off. What was used in the Le Rhône instead was a slipper bearing setup. The crankpin had a grooved hub with 3 circular grooves, and each groove held 3 connecting rods, spaced so their feet could slide without making contact. Despite this added complexity, the Le Rhône 9C was very successful and over 10,000 were built. They powered the Voisin Type L pusher biplane when the war started, and also popular World War I fighters like the Sopwith pup. The 9C produced 80 horsepower from 10.9 liters of displacement weighing 122 kilograms, and the 9J variant, easily identified by its induction pipes at the rear, produced 110 horsepower with a dry weight of 147 kilograms. Time between overall was not quite 50 hours, but exceeded that of the Gnome engines. Importantly, a license-built version of the 9J, the Oberursel UR2, was used on German aircraft like the famous Fokker DR1. The Clerget was perhaps the most conventional of the rotaries. It produced 130 horsepower at 1250 rpm from 16.3 liters, weighing 173 kilograms. It used a conventional master and articulating connecting rod setup. It also had 2 push rods, one for intake and one for exhaust. This allowed valve overlap, useful for increasing performance, and it was throttleable through its block tube carburetor. One outdated feature on the Clerget was the use of an obturator ring, intended to improve sealing with cylinder distortion caused by unequal cooling. This was because the downstream side of the cylinders got less cooling than the upstream side. Obturator rings needed frequent replacement and were prone to breaking. When it did, the engines overheated and usually seized. This problem wasn't unique to the Clerget, but it was heavily affected by it. When motorcar designer Walter Bentley visited one of the factories licensed building the Clerget in Gwens, he made several suggestions to fix the problem. There was reluctance to implement these changes, as they were only a licensed builder, not the engine's designer. Bentley subsequently decided to design a brand new rotary, inspired by the Clerget's design features and addressing most of its problems, including replacing the problematic obturator ring with conventional piston rings. This led to the ultimate rotary engine. Those already familiar with rotary engine history may say that the Siemens-Halske was the ultimate rotary, but I'll cover why, in my opinion, they really removed the best feature of the rotary in order to overcome its limitations. The Bentley rotaries were generally considered noticeably more reliable than the Clerget. The BR.I produced 150 horsepower and replaced the Clerget on some Sopwith F1 Camels, specifically those used by the Royal Naval Air Service. The BR1 led to the BR2, initially producing 230 horsepower, then 250 horsepower from a nearly 25-litre engine weighing only 220 kilograms. That gave it a power-to-weight ratio of 0.51 horsepower per pound. The BR2 powered what was arguably the best fighter of the war, the Sopwith 7F1 Snipe, intended to replace the famous Sopwith F1 Camel. But since it came into service just weeks before the end of the conflict, it did not have any impact on the outcome of the war. Before covering the Siemens-Halske Sh.III, let's look at the drawbacks of rotary engines, as that may help the design of the Sh.III make more sense. Rotary engines have various drawbacks. Since the whole engine is spinning, it's virtually impossible to have a wet sump oil system. So, rotary engines used an external oil tank. Normal lubrication methods won't work, as centrifugal force pushing everything outward doesn't allow oil to be collected and scavenged. This is part of the reason rotaries are sometimes thought to have been two-stroke engines, as they had a total loss oil system. No oil could be recovered. But this is false, they were four-stroke engines. By the way, if you want to see the rotary in more detail at a parts level, check out Pierre's channel. He gave me permission to use his excellent animations in this video. Links in the description. Go show his channel some love. Oil was injected directly into the crankcase. They used castor oil, the only oil at the time that had the lubrication properties required. Castor oil didn't dissolve into the fuel mixture but was pulled into the cylinders by centrifugal force. Some oil was partially burned during combustion, and any unburnt oil exited with exhaust gases. The rotary engine couldn't use an exhaust manifold to redirect these oil-laden gases away from the airframe. There were no exhaust pipes or valve covers. It simply flung exhaust gas and oil out when exhaust valves opened. Approximately 2 gallons of oil was flung out of the engine per hour. Since oil is flammable, it was not a good idea to spray the whole airframe with oil, so a cowling was placed around the engine, with an opening at the bottom where accumulated oil could drain. But the cowl didn't catch all the oil-rich exhaust gas, some of which the pilot inhaled. Since castor oil is a laxative, this occasionally produced some interesting scenarios. Even so, this was not the biggest problem with rotary engines. Neither were gyroscopic forces, nor that they couldn't be throttled. Most could. The biggest problem was drag, in this context often called windage, a direct consequence of the spinning cylinders. When the rotary engines first became used, the airplanes they powered were very slow. By the start of World War I, emphasis was on maneuverability, not speed. But as World War I progressed, the advantage of superior speed became clear and the limitations of rotary engines started showing. Spinning cylinders have more drag than stationary cylinders because they're moving through the air much faster than the airplane is. The cylinders don't only move forward, but they also spin. So the airplane's forward speed and the cylinder's spinning speed both contribute to the effective airspeed of the cylinders. The engine itself is directly pushing against the resistance of air to create power, an issue no other engine type has. Since drag increases with the square of airspeed, the faster a rotary engine airplane flies and the faster the engine spins, the bigger this penalty becomes. With mid-1910s technology, there were really only two ways to increase engine power. One was increasing engine RPM, since horsepower is effectively torque times RPM. But as already explained, we can't increase RPM. The other way is increasing torque, most effective through increasing displacement. But this means bigger cylinders or more cylinders. Both add mass. While rotary engines were comparatively light, increasing weight increased gyroscopic forces. This in effect placed a cap on how far the rotary engine could be developed. Some pilots flying modern rotary replicas remark that gyroscopic effects are barely noticeable. But we have to realize that peacetime recreational flying and flying in combat are not the same thing. Gyroscopic effects are minimized when keeping pitching and yawing movements gentle. In a dogfight, using aggressive stick movements like your life depends on it is when these effects could catch pilots off guard. especially newer ones. The most experienced pilots could even use this to their advantage. You'll often hear claims that rotary fighters could turn left very quickly, but a right turn was slow, or sometimes even the other way around. If turning means banking, this is completely wrong. Any plane with a clockwise turning propeller, as viewed from the position of the pilot, rolls slightly better to the left due to engine torque, not gyroscopic forces, but this effect is minimal. What actually made them difficult to fly was gyroscopic precession. A spinning gyroscope wants to keep pointing at a fixed point in space. The heavier it is and the faster it spins, the stronger its resistance. But it's not infinitely strong. If you push on it, it reacts in a predictable way called precession. A torque applied to it causes it to tilt in the same direction as the push, but 90 degrees of rotation later. On a rotary engine airplane, lifting the tail on takeoff effectively pushes on the top of the spinning engine and propeller. Since it spins clockwise, the reaction yaws the plane to the left. All propeller airplanes are affected by precession, but it's much worse on an airplane with a heavy spinning rotary engine. This didn't only affect the plane on takeoff when lifting the tail, but also in flight. It's quite easy to work out the effect when remembering that the gyroscopic reaction to any movement is 90 degrees of rotation later in the same direction. Imagine this is a Sopwith camel converging head-on with an enemy. As they pass, we want to get on their tail, so we bank right, which, along with right aileron, requires right rudder, causing a slight right yaw, which causes a nose-down pitching moment, compounded as the bank reduces lift and needs back stick pressure to compensate. Pulling back causes a pitch-up moment, for which the gyroscopic reaction is a yaw to the right. So a sustained hard right turn needed some left rudder to keep the nose from dropping. Turns to the left were probably worse. Banking lowers lift requiring a pitch up. This yaws the plane right, so left rudder is required to compensate. But left rudder causes left yaw, which causes a strong pitch up moment. Countering by pushing down causes a pitch down moment with a gyroscopic reaction of a yaw to the left. Even a simple loop wasn't straightforward, as pitching up causes a yaw to the right. An experienced combat pilot would be very aware of these reactions and know how to counter them. With all of that covered, we can now look at what was supposed to be the ultimate rotary engine, which reduced these massive drawbacks. With the limitations of rotary engines clear, an attempt was made to lessen these effects. The Siemens-Halske Sh.III was Germany's only original design rotary engine that saw World War I combat. As discussed, the biggest problem of rotaries was the massive drag caused by the spinning cylinders, which also reduced engine power and didn't allow much increase in RPM. The fastest spinning rotary reached only 1400 RPM for this reason. The designer's idea was to increase engine RPM and reduce the spinning speed of the cylinders. By reducing the cylinder's speed to 900 RPM and having the crankshaft spin in the opposite direction also at 900 RPM, they created a counter-rotary or bi-rotary engine. The engine's effective speed was thus 1800 RPM, while the cylinders only spun at 900 RPM. This reduced drag, allowing an increase in engine power and aircraft speed. It also reduced gyroscopic effects, allowing them to increase from 9 to 11 cylinders. This was done using a set of gears at the back of the engine, allowing the crankshaft to spin in the opposite direction of the cylinders. Now, I need to be clear. The purpose was not for the crankshaft to cancel out some gyroscopic forces. The purpose was to allow the crankshaft to effectively spin faster and the cylinders to spin slower. Another benefit was reducing the propeller's speed, making it more efficient. In theory, this was all a great idea, but it created its own problems. Since the cylinders spun slower, they didn't cool as effectively as conventional rotaries, resulting in overheating and seizures. Part of the issue was that Germany didn't have access to enough castor oil by this time, and there wasn't a good replacement oil with the lubrication properties required. Initial SH3 variants produced 160 horsepower and some variants produced up to 240 horsepower, but this just made the overheating problems worse. Compared to the 250 horsepower Bentley BR II, which was comparatively very reliable, the SH3 just couldn't compete. So in my opinion, the price of ultimate rotary can't go to the SH3, but instead goes to the BR II. The irony was that fixing the overheating problems caused by the slower spinning required improvements in metallurgy, the same improvements that solidified the obsolescence of rotary engines, as they allowed the rise of the air-cooled radial. Advancements in liquid cooling, especially the use of ethylene glycol as coolant, allowed better cooling and smaller radiators. This allowed liquid-cooled engines to effectively replace rotaries even before radial engines did. By 1918, inline engines like the Hispano-Suiza and 400 horsepower Liberty V12 offered more power with better fuel economy and the ability to scale up, while metallurgical advances enabled air-cooled radials by the early 1920s. For a short time though, the rotary engine was unquestionably the best aviation engine type in the world. I hope this video was informative. Let me know in the comments what you think about the rotary engine. Thanks for watching. See you in the next one.